In this figure, showing the changing physics that was happening in the universe as space expanded and cooled, there are two more events that we have yet to discuss. Neutrino transparency, that occurred when the universe was about 2 seconds old, and transparency of light, which occurred when the universe was about 380,000 years old. The transparency of the universe to a particle means that once that particle was free to travel all the way through space, we could examine its relics today for hints, for information about what was happening in the universe back in the earlier times. For neutrinos, the ones that were free to roam through the universe beginning at an age of 2 seconds, should still be with us. Unfortunately, neutrinos are notoriously difficult to detect, and those original neutrinos from the Big Bang time even more so because their energies would be very low. But as you already know, the photons from the early universe we detect as the cosmic microwave background. Labeled in the graph where it says transparency point for light is that moment where the ionized plasma of hydrogen had electrons combining with protons to make neutral hydrogen atoms, and the universe became transparent to photons, photons which then were subject to a redshift of more than 1,000-fold before reaching us today as the cosmic microwave background. Shortly before the universe became transparent to photons, there was another very important event. Matter dominated over radiation. Recall from lecture that the energy of photons diminishes more rapidly than the energy stored in matter. So there came a moment where matter became a much stronger player in the dynamics of the universe than the photons, what we call radiation. That crossover point between when the universe was dominated by radiation and photons ruled the roost, to when the universe was dominated by matter and most of the energy content of the universe was locked up in mass, happened when the age of the universe was about 72,000 years. Give or take 1,000, we guess. 72,000 years is before the universe became transparent at 380,000 years. So what started to happen when the universe was 72,000 years that couldn't have happened before? Matter began to clump together under the influence of gravity. Where there were slight enhancements in the density, where there was just a little bit more matter, the matter was now free of the hindrance of photons to start coming together by natural gravitational attraction, to clump up. And as the material clumped up and fell in on itself, making higher density bunches, the gas in the early universe responded with ripples, acoustic waves, sound waves, rippled through the ionized plasma of the early universe. Sound waves that today can be seen in the pattern of anisotropies on the cosmic microwave background. The larger structures that we see in our image of the cosmic microwave background are a residue from the time of cosmic inflation. It is the much smaller structures, which are the result of the sound waves that began to travel through the original plasma of the universe when matter first became dominant over radiation. In particular, there's a certain blob size of about 1 degree wide that originated from those waves. So this is an analogy, rocks being dropped into water, sending ripples in all directions, that's similar to what happened in the early universe when density perturbations collapsed on themselves gravitationally and sent sound waves from multiple sources, all careening through the ionized plasma of the early universe. Then, when the universe became transparent, our image of those ripples became frozen in time for us to view. In this all-sky image of the cosmic microwave background, the red band across the middle is the Milky Way galaxy obscuring our view, But where we have a clear view of the cosmic microwave background, the pattern of the original ripples from the original sound waves still present, still showing. And that is a wealth of information about exactly what was going on in the early universe at that time. Here again is an image of the microwave sky with the Milky Way galaxy subtracted. Teams of astronomers have studied this image to the finest levels of detail, counting up the blob sizes and running statistical analyses to determine exactly which sizes are more prevalent and to what degree. The result is a graph that reveals a tremendous amount about the contents of our universe. This graph is called the power spectrum of the cosmic microwave background. The horizontal scale lists angular size, from 90 degrees wide, which would be a span across a quarter of the entire sky as we would see it from one place, to angular sizes of a tiny fraction of a degree, the smallest little irregularities in the all-sky image. Notice that there is a tremendous peak in the graph at an angular size of about 1 degree. What does that peak mean? The vertical scale, in fancy units, is a measure of how deviant from the average features of that size are. It turns out that the most common blob size in the cosmic microwave background is about 1 degree wide. This is called the first acoustic peak. This is a very abstract-looking graph. As the authors of your textbook say, nobody understands it at first glance. It takes a while to think about what the information is showing. Again, the horizontal scale, angular sizes, from larger at the left to smaller at the right. The vertical scale, amount of temperature fluctuation. The higher the graph runs, the greater the temperature fluctuations are at that particular angular size. As for the features of the graph, well, they reveal so much about how much matter, how much radiation, how much dark energy, how much of different kinds of matter, what the densities were of the gas, and so on. Let me just show you one example of what happens if we change something about the universe. What effect will that have? For example, this animation is showing what would happen to the CMB power spectrum if the proportion of matter in the universe was raised or lowered. If the universe had more matter, the CMB power spectrum would look like it does when the pink bar is high. If the universe had less matter and more radiation or dark energy or other things, then the CMB power spectrum would look closer to what is shown when the pink bar is lower. By fiddling with the pink bar until we actually get a CMB power spectrum that matches observed reality, we can independently measure what proportion of the contents of the universe is matter compared to other kinds of energy. Returning to the actual power spectrum, let's examine carefully what each of its distinct features tell us.